Welcome everyone. I hope that you can hear me correctly. Welcome everyone to this colloquium, of the Institute of Cosmos Sciences. And today we're really very pleased to have with us Netta Engelhardt. Netta is a theoretical physicist. She's an Israeli-American theoretical physicist who graduated from Brandeis. She got her BSc from Brandeis in 2011, I think in physics and maths, right? And then she moved to sunny Santa Barbara, to University of California, Santa Barbara for her PhD. And then she obtained her PhD in 2016 under the supervision of Gary Horowitz. And it was a brilliant PhD thesis that she presented and defended. Then she had a postdoctoral stint at Princeton University. And in 2019, she joined the faculty of MIT, of Massachusetts Institute of Technology. You might think that she looks very young for a university professor, and well, I mean, she is very young. That's okay. So she looks what she is, and well, you shouldn't be surprised that she's got this faculty job at one of the top places in the world of theoretical physics. She's been, well, her work has been recognized in many ways. She got the Blavatnik Award for Young Scientists. And well, perhaps more impressively, she got one of the fundamental physics breakthrough prizes, the New Horizons in Physics prize last year. And I think that the quotation for the prize was that was for calculating the quantum information content of a black hole and its radiation. Now, I mean, this is information that you can find in Wikipedia if you want, but maybe I like also to say something that you can find in Wikipedia, because, well, I can also say some things from what I know. Well, Netta is one of the people who have made some of the crucial advances in recent progress on understanding all the vexing problem of where does the information about things that go inside a black hole, where does this information go? Does it disappear? Is it lost? It's a problem that was first formulated by Stephen Hawking more than 40 years ago. And as I said, there's been recent dramatic progress. And Netta has been one of the key participants in this progress. She was one of the co-authors of a paper in 2019 where, well, there was, I think it's fair to say that it was the most important advance in at least 25 years since the breakthrough on understanding quantum physics of black holes from string theory. And it's not only that she was one of the co-authors in one of these breakthrough papers, but these breakthroughs were based on an idea, a concept that she had introduced a few years before in collaboration with Aaron Wall, something that's called the quantum extremal surface. As I say, that's one deep, important, and central ingredient in all of this progress. So, I mean, I think it's our not only our pleasure, but our honor also to have one of these persons who have been key in these developments. So, well, I mean, without further ado, I will give the floor to Netta, and let's then enjoy.
Thank you very much, Roberto, for such a lovely introduction. It really is my pleasure to be here and to talk about the black hole information paradox and the recent paradigm shift and really the renaissance that has started in the past couple of years in our understanding of the information paradox. And these recent developments have really, they've really been accelerating. They've started partly as a result of tools that have been developed over the last 15 years or so in the field of holographic entanglement entropy. And so I view this, this new era of the black hole information paradox as, in some sense, the age of holographic entanglement entropy, hence the title of this talk. So let me begin with a little bit of sort of a step back in discussion of black holes. So this is a quote from Franz Cordova, who's director of the NSF here in the US, that black holes are the most mysterious objects in the universe. And I find myself in complete agreement with that statement. Here's a beautiful image from the LIGO collaboration of a black hole coalescence, which was a huge step forward in our understanding of black hole mechanics, especially the black hole exterior. Now, in 2020, the Nobel was awarded for black hole physics, for discoveries in black hole physics, for 2 different discoveries, and that's really reflecting how interesting and important black holes are in physics. So why do we care so much about black holes? I think you'll ask 5 different people who work on black holes, and you'll probably get 10 different answers. For myself, the reason that I care so much about black holes is that they serve as a stage for gravitational phenomena that we don't understand. There's a lot that we don't understand about physics today, and black holes are really a good laboratory for that physics. For example, very deep inside black holes, another example of this is the pre-inflationary universe. General relativity as a theory breaks down. And the reason for this, the reason that we expect this to happen, since we haven't observed it, is that general relativity is not a complete theory of gravity. It's a theory, GR is a theory of very massive objects, and it works really well as a theory of very massive objects. It describes our universe on large scales exceptionally well. But we also have another theory, which is quantum field theory, that describes the really, really small stuff. And of course, these 2 theories don't a priori look like they ever have to do anything to do with one another, because well, GR is a theory of exceptionally massive objects, and quantum field theory is a theory of very small things. But when you have a very massive object like a black hole, which is, so much mass concentrated into a very small part of space-time, you get space-time being curved on quantum scales, then we need a theory that combines the 2, a quantum theory of gravity. And GR just doesn't cut it. Now, we need a quantum theory of gravity to describe what happens inside black holes, but the snag, of course, is that we don't really have one. And I put an asterisk here on the really. And this asterisk turns out to be extremely important for this talk, and is the main reason for me to be able to give this talk in the first place, because there is a qualification here that allows us to make a tremendous amount of progress on black hole physics and the black hole interior. I do want to emphasize for now, before talking about this asterisk, that it is a problem that we are not able to describe the black hole interior at this point. Black holes do exist, and that means that it's not some theoretical, hypothetical discussion. Our description of the universe is incomplete without a theory that accurately describes what happens deep inside black holes, because black holes are real phenomena. And so this is an urgent problem that we really do need to solve. So this brings me to the information paradox, which is very, very exciting in that it tells us that something that we're doing in the way we think about quantum gravity in the black hole interior is wrong. So it comes from the following expectation, which is very reasonable, which is that in a regime where space-time is not very curved, the universe should be pretty well described by just perturbatively interacting GR and quantum field theory, what we call semiclassical gravity, so that we just have very few interactions between them, and we don't expect that the predictions of GR have any impact on the predictions of quantum field theory in this regime, because these theories are really separated by scales. And this is, for example, the regime near the event horizon of a large black hole. Curvatures are small. We expect that this semi-classical limit where quantum field theory and GR are weakly interacting is valid in such area, in such locations. What's so important about the information paradox is that it's an apparent contradiction between the predictions of gravity and the predictions of quantum mechanics at the event horizon of a black hole, where we do not expect that the predictions of these two theories should have anything to do with one another, much less conflict. So again, if the event horizon were a regime where strong quantum gravity effects are always important, then this wouldn't be a paradox. We would just say semiclassical gravity is not valid. There's no reason to expect that we can write down this weakly coupled description, and we just need strong quantum gravity to deal with this. But this is not such a regime. This is not what we expect. This is a regime where we expect semiclassical gravity to be valid. And the predictions of quantum mechanics, as I said before, should not have significant impact on the predictions of gravity. There shouldn't be this large interaction between them because we think that this should be described by weakly coupled quantum field theory and GR. At the same time, we have this paradox that tells us that somehow these have significant impact on one another. And that, of course, is very puzzling. So here is the sort of elevator pitch on the information paradox. It's 30-second pitch, and of course, I'll talk about it in much more detail. So the caricature is that you have two particles, and we affectionately call them Alice and Bob, which are entangled. And we have imagined that Alice jumps into the black hole, falls across the black hole, somehow in some way or other ends up inside the black hole, and Bob doesn't. And then we say, well, it appears the black holes evaporate. So if the black hole evaporates, then even though initially Bob was entangled with Alice, when the black hole finishes evaporating, Bob is now entangled with a particle that no longer exists in the universe. And this is, for reasons that I will explain later, this is indicative of information loss. This is something we consider to be loss of information. And I'll explain more intuitively why that's true later. But for now, let me just say that this is a violation of unitary evolution of quantum mechanics. Unitary evolution of quantum mechanics does not break entanglement, but black hole evaporation, at least naively, appears to do so. So what gives? Well, we've never seen violations of unitarity, but then again, we've also never seen violations of GR. Now, one perspective one could take on this is that information loss would be truly catastrophic. It would mean that physics at its core is actually not deterministic, or in particular, it's not post-dictive. So if we're given the state of the complete universe, of the entire universe at a given moment in time, say right now, we would be unable to determine the state in the past. And that would be a breakdown of determinism of physics, which is incredibly problematic, which is one of the reasons that many of us subscribe to unitarity and information conservation. Either way, black holes exist. There's a definitive answer about whether information is lost or conserved, and we need to figure it out. And one of the reasons that we need to figure this out is because the information paradox has a lot to teach us about quantum gravity, about what we're doing wrong with quantum gravity, about how we're thinking about things differently, how maybe we need to shift some perspective in how we're doing things. Of course, there's a bit of a potential catch-22 here, which is that we have to somehow make progress on the information paradox without first having a quantum theory of gravity that tells us how it's resolved. So this is one of the things that, of course, makes this very challenging, getting a better understanding of the information paradox. So I mentioned in the beginning that there was a paradigm shift in the past couple of years and a huge renaissance in the work on the information paradox, which sort of raises the question of what happened in 2019. So let me tell you the sort of pre and post 2019 perspectives. So before 2019, I would say many of us thought that non-perturbative quantum gravity was necessary in order to see evidence of information conservation in the black hole evaporation. That you simply needed to have that theory, and maybe there was no way around that. The conventional wisdom was that semiclassical gravity just appears to be losing information, and somehow, in some way, quantum gravity fixes it up, maybe as non-perturbative corrections somehow add up. The big difference, the big change in 2019, these results that started in May 2019 and still developments are still ongoing, are actually a purely semi-classical analysis that is a smoking gun signal of information conservation. So this is an analysis, a calculation that can be done just in weakly coupled general relativity and quantum field theory. And I think that it's safe to say that most of us thought that this was impossible. And the fact that it was possible is one of the reasons that this has been such a breakthrough in results and in terms of our understanding of what is happening in the information paradox. So that was the sort of the bird's eye view of what the perspective is on what's going on. And in this talk, I'm going to begin by giving an overview of the information paradox itself, something a little bit better than the caricature of Alice falling into the black hole. And I'll explain in some sense where it stood before 2019. Now, before I move on to what happened in 2019 and afterwards, I'm going to have to go through the tools that were so necessary in order for us to make that progress. And so that will take us on a detour to the age of holographic entanglement entropy. And then I'll tell you about what has been happening since, what happened in 2019, what has followed that, and not just what's going on now, but where I think that we're going. But we'll begin with the information paradox as it was initially formulated. And really we'll begin, as most good stories in physics do, with thermodynamics. So this is a very famous Gedanken experiment. So you imagine that you have a black hole. So you have a black hole, right? And in classical general relativity, a black hole has no microstates. And if black holes have no microstates, then they have no entropy. And so if you take a hot mug of tea and you throw it into a black hole, then it would appear that you have decreased the entropy of the universe, since your hot mug of tea initially had some entropy. This is called Wheeler's Gedanken Experiment, because it was Wheeler who originally devised it. And the way the story is told, that Wheeler was bothered by this, and so he decided to give this problem to his graduate student, Jacob Bekenstein. So for the graduate students in the audience, if you think that your advisor is being a little hard on you, just remember that he or she could have given you this problem. Now, this is a real problem, and Wheeler was quite worried by it, because to summarize in the eternal words of Sir Arthur Eddington, if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. So if we can decrease the entropy of the universe by throwing cups of tea and galaxies and anything else we want into black holes, it would appear we're in violation of Eddington's edict, and maybe GR should be collapsing in deepest humiliation. Well, we'd prefer for it not to. And so Bekenstein really rose up to the challenge when he was given this problem as a graduate student. He said, okay, here's a resolution. Black holes actually are literally thermal objects. They have a temperature. They actually have an entropy. And yes, maybe it looks like they don't have microstates in classical GR, but they have microstates in quantum gravity. And so this thermodynamic entropy is a consequence of quantum gravity microstates. And it is given by the area of the event horizon over 4gh bar. This was, this is really truly a brilliant insight. And it's kicked off a modern black hole mechanics as we know it today. Now, just to comment on the temperature here, because that will be one of the more important aspects of this for us today. For a black hole that's close to equilibrium, we expect the temperature to be inversely proportional to its mass. One aside here about the necessity of quantum corrections for this story to hang together. I want to make it clear that this idea of Bekenstein's doesn't make sense as anything more than an analogy in purely classical gravity, because objects with a temperature have to radiate, and black holes in classical general relativity are perfect absorbers, which means that in order to calculate, say, the temperature of a black hole, you need to work with semiclassical gravity. You have to include quantum corrections so that you don't have black holes being perfect absorbers. And you can do this in semiclassical gravity, which was one of Hawking's one of his major discoveries, certainly not the only one, the computation of the temperature of a black hole. So black holes are thermal, they radiate. And if the temperature of a black hole is hotter than its ambient surroundings, then as it radiates, it shrinks in size, it loses mass. But then we have this counterintuitive thing that the temperature is inversely proportional to the mass. So as the black hole evaporates, it gets hotter. And so it doesn't stop evaporating. It just keeps on evaporating until it is completely gone. So you might ask, okay, well, where are those evaporating black holes? Maybe let's talk some numbers, temperatures of astrophysical black holes. And also maybe just some numbers to see what kind of scales are we looking at here. Well, Sagittarius A star has a temperature, a Hawking temperature of about 10 to the minus 14 Kelvin. That's not a black hole we're going to see evaporating anytime soon. Now, a solar mass black hole would be at about 10 to the minus 8 Kelvin, still very cold. The black holes have to be quite small in order to be warm or hot. A lunar mass black hole would be approximately at equilibrium with a cosmic microwave background. And in case you were curious, a coronavirus-sized black hole would be approximately at room temperature. So these are the numbers on black holes and black hole evaporation and what their temperatures are. So it has to be quite small to be evaporating in our universe. So I find that it helps to see sort of a pictorial illustration of what's going on here. So let's suppose we have some, first let's look at a collapsing black hole. So we have time running up here. And we have some, so here I'm suppressing several directions. So we imagine we have some sphere, this circle here. It's meant to illustrate some star, some sphere, some ball. And this, we're imagining this is sort of collapsing under its own gravitational field. And until eventually it forms an event horizon, it collapses down into a singularity. So this is sort of the 3D illustration of a collapsing black hole. So that's the collapse part. Of course, we're interested here in the black hole evaporation part. So what happens for the evaporating black hole? And how do we think about this? Well, here I've drawn a picture of moment of time. This is sort of a black hole. It's already formed. The collapse has happened. We're looking at the event horizon at some time. And these are all, you can think of these as bell pairs, if you like. These are particles. You can think of them as just pair production, or really just particles that are entangled with one another. Now, you can imagine this one here, which is outside the black hole, sort of leaves the black hole. And the other one remains, because it's behind the event horizon. And so via this process, we say the black hole is radiating these particles that are nucleating, or some of them is falling across the horizon, the other is moving away. And this is resulting in radiation from the black hole, thermal radiation from the black hole. Black hole radiates, it gets smaller until eventually it explodes. And in fact, Hawking's original paper on this was called Black Hole Explosions. So this is a sort of a time extended in the vertical direction. So here we have two particles, one of which ended up in the black hole, the other ended up outside the black hole. This is the event horizon. We imagine the black hole might have formed from collapse sometime earlier over here. And then the event horizon shrank as it evaporated, and eventually the black hole disappeared in some massive explosion. So this is the mechanics of the evaporation process. And the paradox that we're interested is the apparent loss of information between the initial state that forms the black hole and the post-evaporation state, the state of the universe up here after the black hole has already evaporated and is gone. Now, to see this idea of information loss, it helps to talk about the entropy of the radiation. And that's sort of the crux of these new developments, an analysis of the Hawking radiation entropy. And so what we're going to do before we introduce the entropy is just briefly discuss the paradox, then I'll introduce the entropy, and then we'll sort of move from there. So here's a very sort of dramatically oversimplified model. It just gives a qualitative idea of what's going on. Let's take an entangled pair of particles. So it's a bell pair. So here it is in a state like this over here. And we imagine this is our Alice of before. And Alice falls across the horizon. So Alice is now behind the event horizon, heading towards the singularity. This is the state of both particles together, since they're entangled with one another. Now, if we wanted to describe just the state of Bob over here, we would have to remove all of what's associated with Alice. And so we can't, because these are entangled, we can't describe it using a vector in the Hilbert space. We have to describe it using a density matrix. So the right particle, the state of the right particle is a density matrix, which is in fact what we call the maximally mixed density matrix. That just means that these particles are maximally entangled with one another. Okay, so that's the setup. And now we bring entropy into the problem. So for a density matrix rho, so again, this was analogous to what we have over here. For density matrix rho, the von Neumann entropy, sometimes called the entanglement entropy, sometimes called the fine-grained entropy, is defined as minus trace of rho log rho. Why is this a useful quantity for us? Well, for one, it's invariant under unitary evolution. Clearly, if we want to be testing unitarity, then we want a quantity that's sensitive to unitary evolution. So the von Neumann entropy is invariant under unitary evolution. It vanishes for a pure state, which is to say for a vector in the Hilbert space, and only for a pure state. And so it will not vanish for a mixed state of, say, the right particle in the previous diagram. And it is also bounded from above by the thermal entropy, which is the entropy of the thermal state. Sometimes we call this the coarse-grained entropy. So these three facts, there are many other facts you can prove about it. It satisfies various nice inequalities and so on. But these three facts are the ones that are important for us today. And now we can talk about why we say information loss when we talk about unitary, the process not being unitary. So very roughly, we can sort of quantify the way the information in a state in terms of the difference between the thermal entropy and the von Neumann entropy. Again, this is just sort of rough intuition. The thermal state is an equilibrium state. It essentially has no information content. And so if this is the thermal entropy is an upper bound on the von Neumann entropy, then we say that this difference is in some sense the information content in our state. And so if a system evolves to progressively larger von Neumann entropy, then this difference is progressively shrinking. And in that situation, we say that information is lost. Again, because we think of this difference, we can't think of this difference as roughly quantifying the information in the state. Now you might say this happens all the time. An open state, an open system is going to interact with its surroundings and it'll settle down to a thermal state. That's what we talk about thermalization. You know, you have a tabletop experiment, you run your tabletop experiment, eventually your state will most likely eventually thermalize. But that's because open systems don't evolve unitarily, right? They're interacting with their environment. It's not a unitary evolution. But the entire universe isn't an open system. The entire universe should be evolving unitarily, since it's not evolving by interacting with some other environment. It's everything that there is. So let's now put all this together, this idea that we're measuring or we're looking at information conservation and information loss using the von Neumann entropy. So in this very simplistic toy model of the Bell pair, the initial state of the pair is a pure state, right? We wrote the psi up here. Go up there. This is a pure state. So the initial state of both of these together is going to have vanishing von Neumann entropy because it's von Neumann entropy of a pure state. After the black hole has finished evaporating, though, Alice is just gone. She doesn't exist anymore. This particle is gone from the system. And so the total von Neumann entropy of the universe after the evaporation of the black hole has finished is just the entropy of Bob, of the right particle, which is not zero because Bob is in a mixed state. In this particular case, it's log 2. And so we find that the entropy has increased. Even though we started out with a pure state of Alice and Bob, we ended up, after the evaporation process is finished, with just Bob in a mixed state. And we have lost information as a result. So we can think about this a little bit more accurately now from the perspective of the black hole, and in terms of just the system of the state of the entire universe, rather than just the state of these particles, these EPR pairs. So let's imagine that we formed a black hole from a pure state. So that means that the entropy of the black hole, the entropy of the universe, was 0 at the beginning when we formed the black hole. Everything is in a pure state. And let's consider computing the entropy of the radiation. So that's the entropy of everything that's outside of the black hole. Well, if we're in a pure state before the black hole is formed, everything outside the black hole is literally everything we have. So that's zero entropy. So we start out with zero entropy. The universe is in a pure state. Then, of course, the black hole forms. Eventually, the black hole starts to evaporate a little bit. The entropy begins to increase. That's okay, because now we are looking at two interacting systems, the black hole interior and the black hole exterior. There's back and forth, well, not back and forth. We can take a particle that can fall across the black hole horizon, which means that the entropy is allowed to increase because, again, we have an open system now. The radiation is an open system. Everything outside of the black hole is an open system. So the entropy increases. It's allowed to increase. That's okay. As the black hole continues to evaporate, the entropy of the radiation continues to increase. But then the black hole finishes evaporating altogether. Now, the entire universe is literally just the radiation, and yet the entropy is no longer zero. And so here in the middle, we're looking at entropy of a subsystem. So it's okay that it's not zero. Here, we're looking at entropy of the whole system, and here we're looking at the entropy of the whole system. And for the whole system to evolve unitarily means that the entropy at the beginning must be the same as the entropy at the end. And so the fact that Hawking found that we start out with vanishing entropy and we end up with non-vanishing entropy for the entire universe, that is a catastrophic loss of information. That is a violation of unitarity. The entire universe evolves from a pure state to a mixed state, and it loses information. And that means that if we were sitting here and we wanted to post-dict the state of the universe here, we would not be able to. So here is a sort of the time evolution picture on the left side and a couple of snapshots of different times on the right side. So before the black hole has formed, this is our star over here. This is the state. So before, this is a pure state on a complete moment of time in the universe. So this is the time extended picture. Over here, this is just the star. Everything is in a pure state. During the evaporation process, we're looking at everything outside of the event horizon. So that means we're computing the entropy of this thing called rho bulk, the state of the radiation. That's everything outside of the black hole. And again, you can see here very clearly in this picture, that's just part of the system. So it's okay that that's not zero. Again, this is a snapshot. Here's the radiation. We're computing the entropy, everything outside of the black hole. And again, that's just part of the system, so it's okay. But then we compute the entropy of the radiation after. Now there's no black hole, and everything outside the black hole is the entire universe. We find it's thermal, and we have lost information going from a pure state to a thermal state. Okay, so a pure state in a closed system evolves to a mixed state, and information appears to be lost. That's what appears to be happening here. So the question then immediately becomes, is quantum gravity non-unitary? Maybe there are corrections that only come in non-perturbative, like e to the h bar or something. Maybe these somehow fix this. And so we could ask, this is the so-called Hawking curve that shows information loss that follows from Hawking's calculation. What does a unitary entropy curve look like? Well, we already said, if it starts out at zero, when the black hole finishes evaporating, it better end up at zero again. And so we know that this has to be non-monotonic. The entropy can increase for a while, but eventually it has to come back down and reach zero again, so that when the black hole has fully evaporated, we have to have zero entropy to match with zero entropy before it has formed. So this curve is called the Page curve. This is the unitary curve of what it would look like, what the entropy of the radiation would look like if it were evolving unitarily. So what's the correct curve for quantum gravity, and how do we calculate it? And how do we calculate it leads me to holographic entanglement entropy. So a little bit of a preview of where this is going. So from the perspective of semiclassical gravity, it's really hard to see where Hawking's analysis goes wrong. It's a beautiful calculation. It's a real tour de force. And it's hard to see where did he make a mistake? So it seems that we need some ingredient from quantum gravity to help us figure out what is missing from Hawking's calculation that would give us unitary evolution. And what we found in these new developments, starting in May 2019, is that you can do a completely semi-classical calculation and get the unitary page curve, but only if you use an interpretation of the calculation that we do using semi-classical gravity, which is inherited from quantum gravity. In other words, the calculation itself is semi-classical, but interpreting it correctly, that requires input from quantum gravity. And that's sort of the beauty of this, that we can do this calculation. The tools required are semi-classical, but the understanding of it, that's where we need to put in some quantum gravity. And what do I mean by quantum gravity? Well, you'll potentially remember the asterisk I put earlier, where we don't really have a quantum theory of gravity, but there's an asterisk there. And the asterisk refers to holography, which is where quantum gravity is going to come in here to help us compute the unitary page curve. So a sort of 20-second introduction to holography here. So ADS-CFT, also known as holography, also known as gauge gravity duality, is a statement that quantum gravity with anti-de Sitter boundary conditions, essentially quantum gravity in a box, is dual to a lower dimensional non-gravitational quantum field theory. Colloquially, we'll refer to quantum gravity in a box as the bulk and to the non-gravitational quantum field theory as the boundary. This is a little bit misleading. The boundary theory doesn't actually live on the boundary of the same space. It lives on a copy of that space. So if you think of this as sort of a cylinder, the bulk, quantum gravity is everything in it, and the dual theory lives on a boundary of a cylinder, but not the same cylinder. So it's not like they're interacting, these two. Now, this is an incredibly powerful statement because it allows us to do calculations in quantum gravity and interpret them in quantum field theory, or alternatively, it gives us a formulation of quantum gravity in terms of a theory that doesn't have gravity, that we have much better control over potentially. One of the tremendous insights that this gives us is about black holes. So we have this duality. Quantum gravity in anti-de Sitter space is really just quantum field theory. And so a black hole in ADS is just another quantum system. It's an ordinary non-gravitational quantum system. And since the quantum system, the boundary theory, the dual quantum field theory is unitary, it's a non-gravitational isolated quantum system, it doesn't have an information loss problem, it evolves unitarily. That means that black holes, being just quantum states in a unitarily evolving quantum field theory, must also evolve unitarily. So ADS-CFT in some sense gives us immediately the answer to whether information is lost or conserved. Information is conserved, evolution is unitary. So are we done? Is that, that's it? It's just ADS-CFT happened in 1997. What's been going on between now and then that this is not enough? Well, it's not really satisfactory because as much as it was reassuring to know that quantum gravity doesn't lose information, we want to know exactly how this happens. What is the gravitational mechanism that allows information to escape? That is what we're really getting at. And so here are the two pictures of the same system. We have this black hole, which is evaporating, starts out as a star, collapses, evaporates. This appears to be pure, this appears to be mixed. And what do we have in the dual theory? We have some quantum state before, which is pure, and we have some quantum state during, and some quantum state after, and all of these are pure. The evolution is unitary, and all of these are evolving unitarily here. So how do we use this picture to understand what is happening in the gravitational language in here that results in unitary evolution? The idea, and this is where we started in 2019. The idea is, instead of using minus trace rho bulk, log rho bulk, where rho bulk here is the state of the Hawking radiation in the in ADS, we want to use the holographic prescription for computing minus trace row boundary log row boundary. This is the quantity that we know evolves unitarily. This is the von Neumann entropy of the boundary theory, which evolves unitarily. But if we use a gravitational prescription for computing it, then that would give us a gravitational calculation of the unitarily evolving entropy. So that would be a semiclassical gravity calculation, and that would give us unitarity. In the terms of the gravity language, which is what we're looking for, right? We already know evolution is unitary. We want to understand that in the language of gravity. Translating minus row log boundary, minus trace row boundary log row boundary into terms that are purely gravitational gives us a way of understanding that. Of course, that means that we have to have a really good prescription for computing minus trace boundary log row boundary, something that we can rely on and that will compute it for us, even including quantum corrections in the bulk. And when we use the correct prescription for this, it turns out, rather remarkably, in my opinion, that you can indeed do the holographic calculation for minus trace row boundary log row boundary. In other words, you can holographically compute the von Neumann entropy of the dual theory and get a gravitational quantity that computes an entropy that evolves unitarily. And that is, again, something that we did not think that we would be able to get within the realm of semiclassical gravity. So how does this work? Well, what we really need is the holographic prescription for computing the von Neumann entropy of the dual theory. And this is given by this equation over here. So given some boundary pure state or density matrix row boundary, dual to a bulk quantum gravity theory with perturbative quantum gravity in it. So in other words, we're assuming now that we have semiclassical gravity in the bulk, that everything is well described by semiclassical gravity. And you want to use this ADS CFT dictionary to compute the von Neumann entropy of row boundary. The prescription is as follows. You take the area of a surface chi, I'll talk more about what chi is in a moment, over 4g h bar. So this here appeared before as the Bekenstein-Hawking entropy, plus the von Neumann entropy of everything outside of chi. So here is a surface chi, and we're computing the von Neumann entropy of the quantum fields in ADS, but not on a complete moment of time, but just outside of chi. This quantity together was called the generalized entropy by Jacob Bekenstein. So this is the generalized entropy of a surface chi. Now, of course, it's not just any old surface, otherwise this would give you vastly different answers for different surfaces. This is a very special surface that we called quantum extremal. What is a quantum extremal surface? It's a surface which is a local extremum of this generalized entropy. And physically speaking, what that means, if you slightly deform the location of the surface chi, then the generalized entropy of chi doesn't change to leading order in the perturbation. So that is what we mean by quantum extremal, sort of a local extremum of this functional, local in perturbations of its location. And this formula, of course, didn't come about from a vacuum. This is a semi-classical generalization of the Ryu-Takenagi formula, the Hubini-Rangamani-Takenagi formula, and the Faulkner-Lefkowitz-Maldacena formula. All of these different formulas are sort of getting at higher levels of generality of computing holographic entanglement entropy, with this one being sort of the most general that applies to general time-dependent spacetimes and includes quantum corrections to arbitrary order in G Newton. Okay, so this is the tool we're going to use. So here we have a map between gravitational quantities, quantities we compute in semiclassical gravity in ADS, and an entropy. And we want to see, what we really want to see is that this is a gravitational computation that gives you unitary evolution of the entropy, the unitary page curve. And that brings me to the recent developments of the past couple of years. So the next couple of slides are based on these papers from May 2019. So we consider an evaporating ADS black hole. I should say ADS black holes actually don't evaporate if they're large enough for us to have any good control over them, because ADS is like a box. So the radiation bounces off the asymptotic boundary and then comes right back in, and the black hole equilibrates. So we had to jump through some hoops to force the black hole to evaporate, essentially by replacing the sides of the box with a cold bath, so that the radiation flowed out and the black hole did evaporate. And so what did we find? So we did a calculation of the von Neumann entropy of this system using the quantum gravity prescription, the semiclassical gravity prescription of quantum extremal surfaces. So what happens? Well, at early times, the quantum extremal surface is the empty set. So early times, this is a one-sided black hole formed from collapse. This is initially a pure state here. The quantum extremal surface, the minimal quantum extremal surface, that's the one of interest for us, is the empty set. And so the von Neumann entropy of the boundary is just the von Neumann entropy of the bulk quantum fields. So there's no change at this point to the Hawking prescription. Now, as the black hole evaporates into the external system, into the cold bath, the von Neumann entropy of this grows. And if you recall, the Hawking curve and the Page curve agree for a time. So far, this is not surprising. But after the black hole has evaporated more than half its mass, a new quantum extremal surface with a smaller generalized entropy than the empty set appears. So it sits slightly inside of the event horizon, which is actually quite important. And this quantum extremal surface has a generalized entropy, A over 4gh bar, plus von Neumann entropy outside of it, that is smaller than just the von Neumann entropy of the empty set. So this is a moment of time. You can see it sits sort of just inside of the event horizon. And now the entropy of the empty set is not relevant anymore, the generalized entropy of the empty set, because what we care about moving forward is the quantum extremal surface. And as we evolve in time, this entropy decreases. So we reached, when there's this turnover, what happens is exactly the peak in the Page curve. And as we evolve forward in time, the nucleation of this new quantum extremal surface forces the entropy to decrease. The generalized entropy begins to decrease. And so we literally obtain the unitary Page curve by doing the calculation with quantum extremal surfaces. And so this is a calculation for the von Neumann entropy of the dual theory. And using quantum extremal surfaces, we find that the entropy evolves unitarily. It's the gravitational, semiclassical gravity calculation of a von Neumann entropy that is unitarily evolving through the black hole evaporation process. So this is remarkable. We were so excited when we figured out that this is what was happening. Couldn't sleep for quite a while. But it's important to sort of try to understand what happened here. Why did this work? So we have this formula. The von Neumann entropy is equal to the area of chi over 4gh bar plus the entropy outside of chi. And this state here, this entropy is computed using the same state that Hawking used. It's just tracing out part of it and instead compensating by adding this area over 4gh bar term. And so, this quantity together somehow with the appearance of this new quantum extremal surface, it computes a unitarily evolving entropy. The quantum extremal surface, it's clearly, it's critical here. It saves the day. And that's incredibly exciting, but the only place where quantum gravity appeared is just in the interpretation of this quantity as the entropy. It didn't appear in any of the steps of the calculation. We didn't need to invoke strong non-perturbative quantum gravity at any stage. We only needed to invoke it in the statement of the ADS-CFT dictionary itself. And so the question that we have to ask ourselves is, why does this work? Why does quantum gravity repackage entropy in this way in terms of quantum extremal surfaces? And what microscopic Planckian physics is responsible for the success of the quantum extremal surface prescription? We understood this thing now, this tremendous thing that entropy is evolving unitarily because somehow it's computed by quantum extremal surfaces. But this is not a time to rest on our laurels. This is a time to understand why this is happening. We had hoped for so long that the breakthrough on the information paradox would teach us more about quantum gravity. And now it's telling us that we need to understand why quantum extremal surfaces are doing what they're doing and why they're so important for the story of unitarity. And so there has been some significant progress on this front. So we might say, okay, we want to understand why quantum gravity repackages entropy in this way. So a natural question to ask is, how do we normally compute entropies? So there's a trick that we often use, say in a non-gravitational theory. You can compute the Venomous entropy using a computational trick called the Replica Trick. This is just an identity here. And this identity makes it easy to compute this. What you do is you introduce n copies of your system. So you have some state, rho raised to the power n. That's the state on the n copies of your system. And you compute this formula. And this gives you the Venomous entropy. So the important thing is that this is the state on n independent copies, are called replicas of the non-gravitational theory. It's a standard procedure for computing Venomous entropies. Now, in ADS-CFT, we actually know how to relate trace rho to the n, this quantity, to the so-called gravitational path integral, which is a quantity. I'm not going to get into the details of it, but it's very analogous to the path integral in quantum mechanics, except instead of integrating over all paths, we're integrating over all possible geometries that can fill in certain boundary conditions. Now, using this idea of Lefkowitz and Maldacena, that trace rho to the n can be computed using the gravitational path integral, you can actually justify this change in the quantum extremal surface from the empty set to this non-trivial surface, and this change which is so critical for unitarity because it leads to the downturn in the page curve. You can calculate it from the gravitational path integral. And there's a justification for this formula from the gravitational path integral, but it comes at a very odd cost. The cost is that the n replicas, even though they're n independent copies of the same system, appear to have non-trivial correlations. And this was quite a big deal when it first appeared because it's very confusing since we don't expect independent systems to be correlated with one another. These are n independent copies of the single quantum theory. They shouldn't be correlated. Which leads me to the black hole information paradox moving forward. So this clearly is revolving around the gravitational path integral, at least one aspect of the current efforts, understanding why the gravitational path integral is so clever that it knows about the quantum extremal surface and what is going on with these correlated replicas. So to be completely honest, the only exact example that we have good understanding of is two-dimensional, dilaton gravity. And there, the gravitational path integral is computing a disorder average. It's doing an average over theories, over couplings. And that is what gives you these correlations between the so-called independent copies. Because once you have an average, then you've lost the right to say everything has to factorize. So that makes sense. In fact, there's another analogous phenomenon that happens in spin glasses, which I could talk more about, but it's a little technical, so I won't get into it unless there are questions in the Q&A. But it's not clear what this means in more general theories of gravity. So in 2D dilaton gravity, we have some understanding that its dual actually does involve some averaging over couplets, an ensemble, rather than a single theory, which is why we are allowed to have this lack of factorization. But in more general cases, in higher dimensional gravity, we don't necessarily expect that this is the case. And so we are still left with a puzzle. But I would argue something is clear. We have pinned down a key ingredient in the resolution of the information paradox. That is the gravitational path integral. We have to understand why it's dominated by these correlated replicas, why these correlated replicas give rise to unitary evolution, what their contributions mean for the gravitational theory. Is it an ensemble average? maybe something else. Maybe there's some kind of non-perturbative corrections that come in to cancel out these correlations that appear semiclassically. And what all of this means for the quantum extremal surface formula in broad generality. So current state of the information paradox, the main spoiler that we haven't solved it yet. There are a lot of things we still have to answer. What entropy is the quantum extremal surface formula equivalently gravitational path integral calculating? In other words, if I just wanted to take a quantum gravity state and compute minus trace rho log rho, how do I get the same answer as the quantum extremal surface prescription is giving me? How do I do this calculation directly? And what does an observer who's sitting outside the black hole actually measure? We could make arbitrarily accurate measurements, have an arbitrarily good computer, quantum computer. If we fed these measurements to our computer, do we find a pure state or do we find a mixed state? Is the path integral doing an averaging of some sort? Over what? And if not, how do we explain these correlated replicas? And perhaps most importantly, where did Hawking go wrong? So far, what we have is a calculation of the unitary page curve in different language, in a different setting from Hawking's original calculation. And we have a way of doing things right, but we still don't understand how to look at Hawking's calculation and say, aha, this is what he did wrong. This is where the information is missing. And in order to truly resolve the information paradox, we have to work to that and to say in Hawking's calculation, that's what he was missing, and that's where the information is. So we have a long way to go, but I will also say that we really have come a long way as well. So thank you for your attention.
Okay. I think yeah. So I'm not sure what so Jorge, shall you or shall I lead the question period?
Why don't you start?
Yeah. Okay. Well. First of all, thank you. Thank you so much. Sorry for this awkwardness after the.
No worries.
This is. Thank you so much for this talk. And yeah. So now we open the floor for questions. There were a couple of questions during the talk in the chat. We didn't interact, but well, one of the questions is how confident are we that we need quantum gravity to resolve these issues?
I would say fairly confident that we need quantum gravity to resolve these issues because Hawking's calculation is, I would say, really, it seems from the perspective of semiclassical gravity. I mean, I can't say that there's no mistake there because you can never say there's no mistake in a calculation, maybe until you've observed it directly in nature. But I would say it's exceptionally hard to imagine where Hawking's calculation goes wrong in the language of semiclassical gravity, that he could possibly have missed something that's already there in semiclassical gravity. My guess is that the information that's missing from Hawking's calculation really is something that we need to look for in quantum gravity. And I mean, the fact that we needed the ADS-CFT dictionary, the fact that we have this semiclassical gravity calculation that Hawking did, which is really a tour de force calculation, is very careful, that gives you information loss. And you have a calculation that has input from quantum gravity that gives you unitarity. I think that's very strong evidence that we really do need input from quantum gravity in order to actually see unitarity. And I think at the end of the day, the evaporation process, especially towards the end, is a very, it's a quantum process. And I don't think we're going to get away with describing it using semiclassical gravity.
Yeah, there's kind of in this question, they were also asking about the energy scale. I think, let me rephrase this question a little bit. And do you think that the resolution requires physics at the Planck scale?
Okay. Yeah, I see.
The Planck scale being the characteristic scale of quantum gravity.
So, I feel like I should be careful making predictions like this, because if you'd asked me before 2019, I would have said, absolutely. We need some physics at the Planck scale in order to resolve this. And of course, at the end of the day, the actual calculations that we did, the physics that we used to do this calculation of the page curve did not need any Planckian. We didn't use any Planckian physics for that. But even though we still needed input from non-perturbative quantum gravity. So even though my knee-jerk reaction is still to tell you that, I think to ultimately really resolve the information paradox, we're going to need Planckian physics. I'm going to be a lot more careful about committing to that right now. And I think that at the very least, we can go a long, long way towards getting a better grasp of it in terms of semiclassical gravity. And I mean, there's been some interesting developments also on the front of computational complexity that probably have something to do with all of this as well.
Thank you. So yeah, there was another question, whether you could explain, somebody who says that his colleagues working on tensor networks for holography say that black holes are error-correcting codes. The question is whether you could explain what they mean. I think that, actually the phrase is that not only black holes, that space-time is a quantum error-correcting code. So if you could...
Yeah, so this is a statement typically made about ADS-CFT, that quantum gravity is a quantum error-correcting code in ADS-CFT. The reason that this is said is because of what the way that we describe the quantum gravity bulk using the dual theory. And so there's this concept called bulk reconstruction. So the idea being that if you have some operator in the bulk and you want to represent it in your dual boundary theory, and of course there are, you expect to be able to do this because the ADS-CFT dictionary tells you that you can that there's a duality between the two. So whenever you turn on some operator somewhere in your bulk spacetime, you expect that there's a representation of that operator in your dual theory. Now, as it turns out, it's not that there's just one representation of it, but actually there are multiple possible representations of it. So it's actually in the sense in which it's protected against erasures. And so in that sense, I'm sort of glossing over a huge amount of literature here, just kind of trying to get the gist of it, which is that the way that we reconstruct operators in ADS-CFT is essentially it is a quantum error correcting code in the sense that you can protect against erasures, and you have features like quantum secret sharing, and all of this is in the reconstruction of bulk operators in boundary language. So that's sort of the very basic idea of what we mean when we say that quantum gravity, ADS-CFT specifically, is a quantum error correcting code.
Yeah, kind of also tying up with this question is how much of this relies on working in anti-de Sitter space, and how much of this can be generalized to black holes in asymptotically flat spaces?
Very good question. So one thing that I didn't have time to talk about is the work that people have been doing in terms of looking at quantum extremal surfaces and their behavior in spacetimes that are not ADS. So you kind of have a couple of different perspectives you can take on that. You could say, I believe in the gravitational path integral. The gravitational path integral has been so monumental and instrumental in having us, in explaining things in quantum gravity to us. It's not the first time. It's not the first time it's proven to be way too smart than it should be. And so you might say, I don't care if it's got anti-de Sitter boundary conditions or other boundary conditions. I'm just going to use the gravitational path integral. And the gravitational path integral in other spacetimes it'll give me the answer again, a quantum extremal surface. That'll give you a page curve. And so you could say, okay, I'm just going to use the gravitational path integral and trust that given how smart it has been in the past, it's going to keep on being smart here. The conservative thing to do, of course, is to say, oh, in ADS-CFT, we know what the gravitational path integral is computing. It's approximately computing a partition function in the CFT, so we have an interpretation of it. But you could just say, okay, I'm just going to use the gravitational path integral because it looks like it knows what it's doing. So that's one perspective you could take. You could also take the perspective that just the quantum extremal surface formula appears to be maybe the fundamental way of computing entropies in quantum gravity. And we're just going to use that formula in other spacetimes. Now, the main thing that going to other types of asymptotics requires is it requires a certain leap of faith. Either you say, okay, I'm going to use the gravitational path integral without knowing what it means. I'm going to use the quantum extremal surface formula without knowing, strictly speaking, what fine-grained entropy it's computing. The nice thing about ADS-CFT is that we have control over the quantum gravity. We have a duality that tells us that the quantum extremal surface formula, the gravitational path integral, they're literally calculating a fine-grained entropy. But I would say that I trust the gravitational path integral. And I think it really is calculating an entropy in other spacetimes. And maybe we don't really know how to understand that entropy as a fine-grained entropy of some field theory just yet. But I trust that it's doing the right calculation. And I think by looking into it in those other spacetimes, we will learn interesting things about what that calculation is.
Yeah, thank you. So another question, let me rephrase a little bit what is in the chat. Is entanglement entropy the only measure that we can use in order to study this problem?
Certainly
the question
not.
is whether it's the only unitary operation, but well, entropy is not a unitary operation, it's quantity.
Yeah, so certainly entanglement entropy is not the only measure that we can use to study this problem. It's a very astute question because it's not necessarily the case that a unitary page curve implies unitarity. A unitary page curve is consistent with unitarity, unlike the Hawking curve. And I used the phrase smoking gun signal because I didn't want to use the phrase, it literally means unitarity. So there should be other things that we should certainly be looking at. And in fact, for non-evaporating black holes, there is another version of the information paradox, which is phrased in terms of the growth of correlators, rather than in terms of the von Neumann entropy. This was initially proposed by Juan Maldacena. So there are other observables that we should be looking at and seeing what is happening to them and what they're doing. In fact, some of the original calculations in late 2019 were done looking at something called the purity, which is not the same thing as the entropy. So there are other quantities. I think it's quite interesting to look at the sort of the large non-evaporating black hole information paradox and the growth of correlations. And because that is a facet of the information paradox, which has started to be explored more recently, but is not quite as, I would say, as has not seen quite as much of a burst of activity as the work on the entanglement entropy.
So maybe I can add something to this. So the page curve, what it implies is that you begin with a pure state and then you end with a pure state. If you can reproduce this, then you know that well, the initial state was pure, the final state was pure, but that's a necessary condition, but it's not sufficient to claim that the operator that takes you from one to the other is a unitary operator, right?
Yeah, exactly.
So then, you have to use finer probes in order to conclude that the mapping was unitary between one and the other.
Yeah, exactly.
So there was also a question about the replicas, whether you could explain a bit more in what sense all these independent copies, the replicas and the replica wormholes in particular, in what sense they introduce different gravitational theories. This is what's asked, and in what way these theories are different. I don't know whether you agree that it introduces different gravitational theories, but I'll let you explain that.
So if I understand correctly, maybe the question is asking about the averaging over coupling and how the different theories are different, if that's what it's asking. Yes. So the perspective in 2D gravity, 2D dilaton gravity, is that at least a sector of it is dual to so-called SYK, Sashtavi-Kitaev theory, which is a theory of random couplings, where the couplings are drawn. If you write down the Lagrangian, it's got these random couplings in it, and these couplings are drawn from some distribution. And essentially, the idea is that then you integrate over those. So different instances will have different values of the couplings, all drawn from some probability distribution. And so the different instances are all they're different in the sense of having different couplings between the sites you could think of. But when we talk about the gravitational description, we imagine that we're doing some kind of an integral, which is averaging over these with the appropriate measure given by the probability distribution.
There was also another question. I think that this is a simpler one. If one started with a collapsing star, in what sense is the initial state pure?
If you prepare it from an initial state, then from a pure initial state, then it will be a pure state. So you could imagine just taking some pure quantum state and you just collapse it into a black hole, right? The entire universe right now at this moment in time is in some quantum state. And if you imagine that it's in a pure quantum state, then the whole thing is pure and the black hole can collapse. Now, I should emphasize that this doesn't hang on the initial state of the universe being pure. You could imagine starting out with an initial state which is mixed. It's a little odd, but you could imagine that. But then you had better end up after the black hole evaporates at the same value of the entropy as the initial mixed state. So you could certainly imagine doing something like that. The reason that we like to use the pure state here is because 0 is a good reference point. But the point of the unitary evolution is that the entropy before the black hole starts to evaporate and after it finishes evaporating has to be the same. Whether the initial state is pure or not, we like it to be pure because it makes our life simpler, but that's not critical.
Don't see no more questions. Let me ask you one question, kind of a broad question, because you began by phrasing the problem of black hole evolution, the unitarity in black hole evolution, as a problem of postdiction, that's reconstructing the past from our present state. Well, that's, of course, that's a big problem for a predictive or for a deterministic theory. But we also know that, well, another big open problem in the theory of gravity is the problem of prediction, and that's the problem of cosmic censorship and the appearance of naked singularities. And it's curious that these two problems, which, as you say, one of them is prediction or reconstruction of the past, and the other one is prediction to the future, they don't seem to be the time reversal of each other, these two problems. And how they are connected or not, that's not very clear. Well,
that's a really fun question. So I agree with you that on the face of it, they don't seem to be connected to one another, but I suspect that they actually are. And in particular, so the evaporating black hole violates cosmic censorship. And moving forwards in time, not also moving backwards, but also moving forwards in time, it violates cosmic censorship. And that's okay. We think that this actually does happen. But as you like to say, the violation is not so bad. And so I want to say that unitary processes in quantum gravity can violate cosmic censorship by some small amount, but there's something about unitarity which is going to prevent large violations of cosmic censorship. And I'm basing this, say, quantum cosmic censorship maybe, and I'm partially basing this actually on recent work with my student, Osman Folkestad, where we showed that trapped surfaces don't lie outside of event horizons in ADS-CFT, but the critical ingredient to that was that local unitaries don't change the von Neumann entropy. And so that was really important for that. And also that, it can evolve, if you unitarily evolve the entropy, it doesn't change. And so I do think that unitarity is actually important for the correct formulation of quantum cosmic censorship, whatever it is. But so that on a very broad scale, I think they are connected actually. But to go from that to saying, how does post-dicting the initial state of an evaporating black hole connect with the existence of Cauchy horizons in Kerr as a Nordstrom? That I don't know.
Yeah, thank you. I don't know if there are any more questions. I don't see anything else in the chat. I don't know whether my other colleagues here also in Zoom, whether they want to voice any question.
No, I don't. I think the seminar was extremely clear, and we have many questions already.
We've had many questions, and yeah, so I think that we've all enjoyed it a lot, learned a lot, and well, I think that we must thank you again. Thank you so much for spending this time with us. And yeah, I think we can now close it.
It's my pleasure. Thank you for the invitation.